Hello friends, myself Dr. Nandakumar Rawale from College of Engineering Ambazogai is going to deal with applied thermodynamics 2. This is our 18th lecture. In previous lecture we have discussed about the psychometric processes such as humidification and dehumidification and methods for obtaining humidification and dehumidification, sensible heat factor, then cooling and dehumidification process, then cooling with adiabatic humidification, and we discussed about cooling and humidification by water injection system. Now today we are going to discuss heating and humidification, then heating and dehumidification, adiabatic mixing of two air streams, then a room sensible heat factor and grand sensible heat factor. So now we are going to discuss heating with humidification. So what this heating and humidification is? So this heating and humidification process is generally used in winter air conditioning to warm and humidify the air. So when air has to be humidified and it is to be made warm, then this heating and humidification process is used. So this process is a reverse process of cooling and dehumidification, which we have studied in previous class. So when the air is passed through humidifier having spray water which is having temperature higher than dryable temperature. So what is the condition is the temperature of water is greater than the dryable temperature of air. So if the temperature of water is greater than the dryable temperature of air, then in this process the entering air which is unsaturated air will reach the condition of saturation. How it reaches the condition of saturation means, so as this air comes in contact with the hot water, the water gets evaporated and by absorbing latent heat of vaporization from water itself, thereby cooling the water. So here this air, when it is passed through the water droplets which are having the temperature higher than dryable temperature, so this outer layer of this water droplet gets evaporated and mixes with air, and this air comes with higher humidity, that is specific humidity, whereas this water droplet is cooled because this water outermost layer of water droplet absorbs latent heat from inner part of water droplet and it gets evaporated, and inner part of this droplet gets cooled. Say for example this is the droplet, so outermost layer gets evaporated, thereby absorbing heat from inner core. So outermost layer gets evaporated, whereas inner droplet will be cooled as the heat is absorbed by outer layer. So this evaporated water gets mixed with the air. So the heat of vaporization of water is absorbed from spray water itself and it gets cooled. In this way the air becomes heated and humidified. So here air becomes heated and humidified means here this water gets added with air, as well as the temperature of air is also going to increase because this air passes through the water having higher temperature than the dryable temperature. So this process of heating and humidification is shown on this figure, that is process 1 to 2 is shown on this figure. So this is the process where the dryable temperature increases from TD1 to TD2 and humidity, that is specific humidity, increases from omega 1 to omega 2. So this is heating and humidification process. The air enters at condition 1 and leaves at condition 2. So in this process the dryable temperature as well as specific humidity both are going to increase. The final relative humidity of air can be lower or higher than the air entering. So it is about the relative humidity. So this relative humidity curves are parallel to this saturation line. So sometimes, so this point may be above or may be below. So relative humidity may be higher or lower, but the specific humidity will be higher than the air entering into this system. Now let us consider MW1, mass of water at inlet or entering, and MW2 is the mass of water leaving the humidifier. Humidifier is nothing but a system where air is passed to absorb water and to increase its specific humidity. So MW1 and MW2 are mass of spray water, entering and leaving the humidifier in kg. Now next we see HFW1 and HFW2. So enthalpy of water at inlet, enthalpy of water at outlet, spray water, we can call this as a spray water. So enthalpy of spray water entering and leaving the humidifier in kilojoules per kg. Then let us consider omega 1 and omega 2 be the specific humidity of the entering and leaving air of the entering and leaving air in kg per kg of dry air. Let H1 and H2 be the enthalpy of entering and leaving air enthalpy of entering and leaving air in kilojoules per kg of dry air MA is the mass of dry air entering in kg. Now for mass balance, we can mass balance of spray water we can write. So mass of water entering minus mass of water leaving, mass of water entering minus mass of water leaving. This difference is responsible to increase the humidity, that is mass of air which was having specific humidity omega 1 increases to omega 2. So omega 2 minus omega 1. So the increase in specific humidity is responsible because of evaporation of mass of water. So therefore mass of water at inlet minus mass of water at outlet is equal to mass of air into specific humidity of air leaving minus of specific humidity of air entering into the system. So therefore this can be written as mass of water at the outlet is equal to mass of water at inlet minus of mass of air into omega 2 minus omega 1. We call this as equation number 1. So this is equation number 1. Only by transferring this mw1 on right hand side and multiplying on both sides by minus 1, we get this equation number 1. So now for enthalpy balance, so what is this enthalpy balance? We have two things. One is the enthalpy of water entering, that is mass of water at inlet, into enthalpy of water, specific enthalpy, that is HFW1 is the enthalpy of water entering, minus enthalpy of water leaving, that is MW2 into HFW2. So this is the enthalpy loss. So total enthalpy of water entering is MW1 into HFW1, and enthalpy of water leaving this humidifier is MW2 into HFW2. So this is the total enthalpy difference. This enthalpy is lost, and that enthalpy is gained by mass of air to increase its enthalpy from H1 to H2. So mass of air into change in enthalpy of air is from H1 to H2. So from this we can call this as equation number 2. Now substituting value of mass of water from equation number 1 in equation number 2, substituting mass of water MW2 from equation 1, we get here as MW1 HFW1 minus of, in place of MW2 we can write equation number 1, that is MW1 minus of MA in bracket omega 2 minus omega 1 into HFW2, and which is equal to MA H2 minus H1. So from this MA, if we transfer on right hand side, then we can write this equation as H2 minus H1. So enthalpy difference H2 minus H1 is equal to, so here we know this MW1 is taken common, MW1 is taken common together, and if we simplify this, then we can rewrite this equation as 1 over MA in bracket MW1 HFW1 minus of MW1 minus of MA minus of MA into omega 1 minus omega 2 minus omega 1 in bracket HFW2. So this can be further written as MW1 divided by MA in bracket HFW1 minus HFW2. So this term and this term multiplied by this HFW2. So MW1 is taken common, so HFW1 minus HFW2 is going to remain, and then minus of this MA into HFW1. If we multiply, so MA and MA gets cancelled. So here MA will go outside. That is nothing but omega 2 minus omega 1 into HFW2. So this 1 over MAW1 divided by MA is multiplied only with this. When we multiply this with this, so this MA gets cancelled, and this HFW is in multiplication. So this is nothing but the increase in enthalpy of air from H1 to H2 in the humidification process. So in this humidification process, we can say that enthalpy increases from H1 to H2. So increase in enthalpy is nothing but amount of heat transfer. Now this total heat transfer Q is given by H2 minus H1. So this H2 minus H1 is the increase in enthalpy of air. So this increase in enthalpy of air is divided into two parts. So this H2 minus H1 is divided into two parts, that is H2 minus HA, H2 minus HA, and plus of HA minus of H1. So here this first part is known as a latent heat and second part is known as sensible heat. So this is nothing but QL latent heat plus of QS, that is sensible heat. So this can be taken and we can write as a sensible heat factor. So this sensible heat factor can be written as SFH, which is equal to sensible heat divided by total heat. Sensible heat is nothing but QS divided by QS plus QL, and that can be written as HA minus of H1 divided by H2 minus H1. This is sensible heat factor. Now proceeding with next part, heating and dehumidification. So this process of heating and dehumidification. So here the specific humidity is going to decrease, whereas heating means dryable temperature is going to increase. So this process is mainly used in industrial air conditioning and can also be used for some comfort air conditioning installations. Now in this case, relative humidity may be low or it may be high, or low dew point temperature in the room. So in this process, the air is passed over chemicals. The air is passed over the chemicals in which the moisture is absorbed. So the chemicals which are used are such chemicals which are hygroscopic in nature, and these chemicals absorb moisture, or sometimes the moisture gets condensed out from the air and it gives up its latent heat. Due to condensation, the specific humidity is going to decrease. So this specific humidity is going to decrease, and heat of condensation supplies the sensible heat. So as the moisture is condensed, so heat of condensation is left into the air, and that increases the sensible heat of air. So thus in this case, increasing its dryable temperature and reducing the specific humidity, so heating and dehumidification process is moved. So this process of heating and dehumidification is shown by the line 1 to 2. So during this process, what we see is the process is nothing but the constant wet bulb temperature process. So this follows the constant wet bulb temperature line or constant enthalpy line, both are the same. So therefore the effectiveness or efficiency of dehumidifier, effectiveness or efficiency of the dehumidifier is given as efficiency of dehumidifier is nothing but actual increase in dry bulb temperature to the ideal increase in dry bulb temperature. So actual increase, if we see dry bulb temperature increases from TD1 to TD3. So actual increase is TD3 minus of TD1, but ideally speaking, so this should increase from 1 to 2. So TD2 minus of TD1 is the ideal increase. So this is nothing but the effectiveness of dehumidifier. Now we'll see this adiabatic mixing. What is this adiabatic mixing? Two streams of air. So stream 1 and stream 2 of air having different properties. So air stream 1 has got mass flow rate m1 having enthalpy h1 and specific humidity omega 1, whereas stream 2 has got mass flow rate m2, enthalpy h2 kilojoules per kg and specific humidity omega 2. So these two streams are going to mix and coming out with mass flow rate m3, enthalpy h3 and specific humidity omega 3. So this is happening here. So let m1 be the mass of air entering at 1, is it? So m1 comma m2 and m3 be the mass of mass flow rate of air at stream 1, 2 and 3, where stream 3 is the mixture of two streams 1 and 2. Then H1, H2 and H3 be the enthalpies of air in the stream 1, 2 and 3, whereas omega 1, omega 2 and omega 3 be the specific humidities of air streams 1, 2 and 3 respectively. Okay, then so now what we can see here for mass balance of air. So for mass balance of air, we can write as m1 plus m2, mass of air entering in stream 1, mass of air entering in stream 2, m1 plus m2 is nothing but equal to m3. We call this as equation number 1. Now for energy balance, so energy entering in the stream 1 is mass of air into h1, that is enthalpy 1. m1 h1 is the energy entering in stream 1, whereas energy entering in stream 2 is m2 h2, and the energy of stream 3 is nothing but sum of these two, which is nothing but m3 h3. We call this as equation number 2. Then for mass balance of water vapor, mass balance of water vapor. So what we can write is mass of air at stream 1 into omega 1, which is equal to plus mass of air in stream 2 into omega 2. So this is the mass of water vapor, which is equal to mass of air in third stream into specific humidity of third stream. So we call this as equation number 3. So this is for mass balance of air, this is for energy balance, and this is mass balance of water vapor present in the air. So now from equation 1 and 2 we can write, substituting value of m3, value of m3 from equation 1 in equation 2, from equation 1 in equation 3 we get, so we get here as m1 h1 plus m2 h2 is equal to m1 plus m2 into h3. So on simplification, this can be written as m1 h3 plus m2 h3. So now from this we can transfer terms containing m1 on one side and m2 on other side. So we can write this as m1 h1 minus of m1 h3, which is equal to m2 h3 minus m2 h2, or this can be written as m1 h1 minus h3, m1 is taken common, which is equal to m2 h3 minus h2, or we can write as m1 divided by m2 is equal to h3 minus h2 divided by h1 minus h3. So this is one equation. We call this as equation number 4, say. So now similarly, substituting value of m3 in equation 1 from 1 in equation number 3, value of m3 from equation 1 in equation 3, we get directly we will simplify, and finally result we will write m1 divided by m2 is equal to omega 3 minus omega 1 divided by omega 1 minus omega 3, so omega 2 here we get. So this is equation number 5, say. So equation number 4 and 5 are same, left hand side is same, therefore we can write a general equation as m1 divided by m2 is equal to h3 minus h2 divided by h1 minus h3, and which is equal to omega 3 minus omega 2 divided by h1 minus h3. So this is the adiabatic mixing. Here we have stream 1 which is mixed with stream 2, and resultant we get as stream 3. So it will be the properties of stream coming out of this mixture is going to lie on the line joining from 1 to 2. So if we know properties at point 1 and properties at point 2, we can have a straight line, and the properties of resultant will lie on this line 1 to 2. Now moving to next aspect, that is room sensible heat factor. What this room sensible heat factor is, we will discuss. So this room sensible heat factor is nothing but the ratio of room sensible heat to room total heat. It is the ratio of, it is defined as the ratio of room sensible heat to the room total heat to the room total heat. So this is room sensible heat factor is nothing but room sensible heat divided by a room total heat, or this can be written as a room sensible heat divided by a room sensible heat plus a room latent heat. So now we can see one thing here. So in air conditioning, supply air is supplied at the property SA, and the room design conditions are at point R. Say it needs dryable temperature TD2 and supply air dryable temperature is TD1. So this is the room design condition, and this is supply air condition. So if we join these 2 points, so we will have a sensible heat factor line, room sensible heat factor line. So what happens here, the condition the air is supplied to the room must have capacity to take up simultaneously both room sensible heat and room latent heat loads. So there are 2 kinds of loads. One is room sensible heat and room latent heat. Thus the point S here is on psychometric chart as shown, represents supply of air condition. So air is conditioned in the process, and that air which is conditioned is having certain properties, and that properties if we mark on psychometric chart, so that properties of those properties of air are marked on psychometric chart, and that point is ESA. And the point R here represents the required final condition in the room. So for example, air is supplied at 10 degrees Celsius, and we want room temperature as, say for example, 30 degrees Celsius. So this is the requirement, and this is the supply condition. So in case of a air conditioning, what is happening here is the air is supplied, or it is recirculated, partially air is recirculated, as well as fresh air is also added into the room. So the line SR here, the line SR is called as a room sensible heat factor. The line SR is known as room sensible heat factor. The slope of this line gives the ratio of room sensible heat to the room latent heat. So slope of this line means angle theta, gives us the ratio of room sensible heat Room sensible heat means this heat, that is, say, enthalpy difference. If we mark point S, R, then P, say. So HP minus HS is the sensible heat, and HR minus HP. HR means enthalpy at point R, and HP is enthalpy at point P, and HS the enthalpy at point S. So this gives us the sensible heat factor line slope. So thus supply air is having its condition given by any point on this line will satisfy requirements of room with adequate supply of air. In other words, the supply of air having conditions marked by point S1, S2, S3 and S4 etc. will satisfy requirements of quantity of air supplied will be different for different supply air points. Now here the supply condition S requires minimum air. Supply condition S requires minimum air, and at point S it requires maximum out of all 4 points. So here it requires maximum, here it requires minimum. So this is nothing but we call as a room sensible heat factor. So this is latent heat, room latent heat, and this is room sensible heat. So this is room sensible heat, whereas this is room latent heat. So tan theta, room latent heat divided by room sensible heat, gives us the slope of this line, and that is room sensible heat factor, slope of room sensible heat factor line. So now this is about room sensible heat factor. So now we will see the grand sensible heat factor. So this grand sensible heat factor is defined as the ratio of total sensible heat, the ratio of total sensible heat to the grand total heat. Grand total heat. Which the cooling coil or conditioning apparatus is required to handle. So now mathematically grand sensible heat factor is given as grand sensible heat factor is given as total sensible heat divided by grand total heat, or this can be given as total sensible heat divided by total sensible heat plus total latent heat. So now looking at this diagram, here we can find the outdoor conditions are marked at point 1. Outdoor condition means outside the air conditioned space, and the room is designed for air conditioning at point 2. Say for example, certain properties are available for the air which is outside air, and in this room we need this condition at point 2. So in case of air conditioning, what happens, the air, some part of air is recirculated from the conditioned space, and some part of fresh air, that is ventilated air, is recirculated. So the air supplied to air conditioning plant is mixture of fresh air, that is outside air, or which is called as a ventilation, and some part of air is recirculated having properties of room air. So here some air is recirculated from room and some air is taken from outside. So these two airs are mixed and mixture is supplied into the room. So the mixture condition of air entering the cooling coil. So this mixture is passed over the cooling coil and then it is processed. So then on psychometric chart it is represented by 0.3. So this 0.3 represents the mixture condition of air entering the cooling coil. when the mixture condition enters the cooling coil, when this mixture condition enters the cooling coil or condition apparatus, it is cooled and dehumidified. This air mixture is cooled as well as dehumidified, so specific humidity is reduced and it is cooled. So this dehumidified, the point 4 shows supply air leaving the condition. So here this point 4, when this air is passed over the air conditioning coil, then the air gets conditioned, that is the temperature is reduced, dryable temperature is reduced and specific humidity is reduced, and that point is marked at 4. So this line from 4 to 3 indicates gross sensible heat factor line. So this line is nothing but grand sensible heat factor line, and this line when produced or extended beyond this, and when it meets to the saturation curve, that point is known as apparatus dew point temperature. This is known as apparatus dew point temperature. If the mixture condition entering the coil or conditioning apparatus and the grand sensible heat factor are known, what we know, if the mixture condition entering the coil, that is condition at point 3, as well as our condition apparatus or grand sensible heat factor we know, then grand sensible heat factor line may be drawn on psychometric chart. So this line can be drawn on psychometric chart in similar way as discussed in room sensible heat factor line. The point 4 shown in this figure intersects the grand sensible heat factor line and our room sensible heat factor line. This point gives ideal condition for supply of air to the room. So this point gives us the ideal supply of condition room or air to the air conditioned room. So this is how we have covered grand sensible heat factor line. So we stop here, and in next class we will be discussing about the various air conditioning methods or air conditioners. Okay, thank you.